Okay, let's start. Good morning to everyone. Welcome to the invited talk by Dr. Lohitzune Solabarrieta with title Ocean Monitoring Using Remote Sensing Platforms. We will start with a short welcome note and then we will proceed to the talk. The talk is recorded, so please turn off your cameras and microphones. We'll allow questions through the chat and they will be answered after the talk. At this point, I would like to invite Dr. Christiana Paputsa, a liaison manager of ERATOSTHENES Centre of Excellence, for her welcome note.
Thank you, Eleni. We are grateful to welcome Dr. Lohitzune Solabarrieta for today's talk. Dr. Lohitzune Solabarrieta is a civil engineer and she got her PhD in the analysis of ocean surface currents using high-frequency radar technology in 2015 at the University of Cantabria in Spain. In collaboration with AZTI-BRTA, she continued her research line as a postdoc in King Abdullah University of Science and Technology 2016 to 2020, and she's currently part of the Marine Technologies Group in AZTI-BRTA. Her research interest is mainly focused on the characterization of the surface ocean processes at different spatio-temporal scales using combining data from remote sensing and in-situ measurements. And she is also interested on the applications of the ocean processes characterization and forecast to the operational oceanography. Thank you, Dr. Solabarrieta, for taking the time for today's talk. And we are looking forward to hearing what you are going to present. Thank you.
Thank you, Christiana and Eleni, for the warm welcome. So I would like to share my screen to share my presentation. Okay, now this was. So can I remove this? Yeah.
Yes.
So can you see it properly?
Yes, thank you.
Okay, so as I was saying, thank you very much for the invitation and for the opportunity to present you the work that we are doing in our group on the ocean monitoring using remote sensing platforms. So this is me who is today here, but I would like to tell you that we are a really multidisciplinary group. I am a civil engineer, as you said. We have biologists, we have ocean scientists, we have engineers, we have technicians, we have data analysts in the team, and all of us, we have different background, and we give our knowledge to the whole analysis or to a complete analysis using different technologies. So as you said, I work in AZTI. It's an ocean research and food research institution. And today I will talk to you about ocean monitoring. So why do we monitor, or how do we monitor? So in this picture, you can see that the ocean, apart from being huge, we have so many different spatio-temporal scale processes going on at the same time. I'm sorry. So from when we go to the beach, we can see the small river input. We can see the tide. We can see some eddies. Sometimes they can be near the coast. They can be offshore. But together with these processes, we have higher processes like mesoscale processes, the big ocean currents that we all know, and we have to monitor them to know what's going on. But monitoring them at right scales is not so easy, because we have processes like from molecular processes that takes few seconds or less than a second, and the spatial scale is few millimeters, to huge spatial scales of more than thousands of kilometers and thousands of years, processes that occur or take thousands of years to happen in the ocean. So as I said, we have the tide, which we see every day, but we have then climate change associated also to ocean processes. So what is the benefit of using remote sensing technology? So a few years ago, we just had in situ measurements. We had buoys. We were used to do campaigns and taking in situ samples, analyzing those samples or measuring currents or visual waves from boats, but they were punctual measurements. And we saw a few years ago, the scientists, they saw that we needed to move on to monitor higher scales. So nowadays we have satellite images, but we also need higher resolution information because some of the processes we cannot measure them from satellite, even the really coastal processes. So nowadays we have radars to monitor ocean waves and currents. We also use coastal videometry, and we can apply the same technology in different ways to obtain the information that we want. So today I will present you these three technologies: radars and high frequency X-band radar and coastal videometry, some of the applications that we use them for. And at the end, I will show you a project that is civil, focused to the civil problems, where we have been capable to include the different in situ remote sensing and modeling capabilities. So the high frequency radars. So the high frequency radars are radars that use the radio waves to measure currents and waves. And the high frequency radars emit from 3 to 30 megahertz. Some of them, they are very high frequency radars, and the frequency can be up to 300 megahertz, but usually we work between 3 and 30 megahertz. And how does it work? Oops. How does it work? So we have one antenna which emit the wave signal to the ocean. And if there are ocean waves with the half of the wavelength of the signal that we are emitting, we receive the signal, and in the spectrum of this signal, we see two peaks. This is called the Bragg effect. And as we know the theory behind the waves, we know where these two peaks should be located. And as you see, there is a difference in space between the dot and the vertical line. So in absence of current, these 2 points, they would be in the same place. But this difference location, it allows us to get the velocity of the currents under the waves that we are measuring using the dispersion relation of the waves. I am not going into the equations because it can be complicated, but it's a theory, the waves theory that it's behind. So currently, there are two main brands that use of high frequency radars in the global market, and the main difference that they have is how they detect the incidence angle of the emitted and received signal. So the WERA system, they use 16 antennas from in each site, and the CODAR systems, they use one antenna, and the information is a bit different. The raw information, the spectral information, but the output is wave and current information. And the accuracy of both of them, there are several papers, it's similar. In some cases, one of them is working better. In some of them, the other one. But they are the two main brands. Nowadays, as the cost it's high, some researchers have started doing low-cost, high-frequency radars. And what do we get? So these are two locations in the Basque Coast, in the northern of Spain. This is the northern coast of Spain. And in each site, here we have two sites, we get the radial velocities approaching or going far away from each of the antennas. But we just have the radial velocities. If we have two or more antennas, we can combine and we can get total currents. And this is something that is a difference from the traditional measurement methods to the remote sensing methods. Because as you can see, I didn't say, but this range is up to 180, 80 kilometers. So every hour we have data, ocean surface and wave, surface currents and waves data over 150, 120 kilometers area. And every hour we have one information. The resolution is 5 kilometers between each of those arrows. So this is an improvement from the traditional methods. And here I wanted to show you that this sounds like a magic, but if we compare the information in using the traditional buoys and the radar measurements, here this animation is hourly currents, so you can see that there is a huge variability in the data. But if we compare over those points the currents, the east-west currents and north-south currents over this buoy and the closest radar data, that they are measuring the same. So we can say that the technology works really, really well. This is just an example, you to see that if we also compare this with satellite temperature images, when we have warmer current waters going to the north, this is the Iberian polar current that is coming from the southwest of Spain through the Atlantic, and it goes to the north. We can see the signal both in the satellite image, but also in the radar. This is a typical wind-driven pattern that is also present in the study area. And these are some more examples. This is an eddy, which also has a signature in the satellite data. We also see a smaller scale eddies present in the area. So what we are measuring with the high frequency radars is also present in the satellite data, which is again another validation, qualitative validation, which confirm the wellness of this data. And due to the spatio-temporal resolution of this data, these data are not only used for ocean research and to analyze the variability of the ocean processes in the study areas, but also for search and rescue management. So in the US coast, especially in the next slide here, you can see this is the US coast, the western and the eastern part of the coast. They have a lot of radars installed in the area, and they use this information for the search and rescue department. They have different frequency, so different range and resolution radars, and they combine all of them. This is the case of Europe, where you see that we also have a lot of high frequency radar antennas installed in our coastal areas, and the same is happening in Asia. So we can say that it's a worldwide technology. We're using high frequency radars, but as I told you, to have this long range study area up to 150, 180 kilometers, we don't have a big or small resolution, and we wanted to have more resolution in the coastal areas. So we started working with X-band radars. The X-band or marine radars, the technology was developed for navigational purposes, for safety, and for safety during nights or bad weather conditions. But this technology is again a radio-based technology. So we, not us, but some researchers, they started thinking on using that to extract wind and wave information in the similar way as done by the high frequency radars. This is just a typical configuration of the X-band radars. And in this case, we, instead of measuring the real waves that we are observing in the ocean, the technology measure the small surface ripple waves that are modulated by the gravity waves. So if there is wind, we can measure this rugosity of the ocean, and we can, again, doing the transformation of the spectra, we can get the information of the waves and currents. In this case, the frequency is higher than with the high frequency radars, so the range is smaller. In this case, we can measure up to 2 kilometers, 3.2 kilometers far away from the antenna. And the challenge in this case is that we can analyze small windows of the image, but if we are in deep currents or in deep waters, all the equations that I mentioned at the beginning, they are constant. But when we approach to the coast, these equations, the waves, they start measuring they can feel in the bathymetry. So we need to be really careful when we apply these equations. And as I told you at the beginning, we just started with this technology to measure wave and currents in the coastal areas. We started 1.5 years ago. We did some tests in October 2021, in December 2021, and last year, 1 year ago, we installed the antenna in the French coast. So we had it working for 1 year, and now we are validating the data. And I didn't put any results because it's just preliminary results, but we can see that we are observing the same variability that we are observing with the models. So this radar, X-band radar data will be used to corroborate what the model was observing. And yesterday we finished the installation of the same radar in a breakwater in the project that I will explain you at the end. But it's again working since yesterday in the Basque Coast. And finally, I would like to talk to you also about the coastal videometry. So this is another remote sensing technology. So what the videometry is doing is just taking images of the coastline, of the coastal areas, and we have several approaches. So if we average the images, the technology allows to quantify the high variability coastal processes. So you can see a single image in the left and an average image in the right. So we can see the coastline. Of course, we have to apply the octorectification to transform these oblique images in a plane metric image to apply all the processing and to get information. So you can see that we can see the shoreline during the different times of the year in the same beach. We can also apply the relation between the energy dissipation and the intensity of the waves, and we can we can see, we can observe what is happening in the water, not only in the coastline or on the beach. So again, more equations to extract the information. We could also take one transect of each image and copy. So this is half of the image, and then you can see how this transect is repeated. And in the right image, we can see this is the seafront, the walking path. And here we can see how the water or the waves are achieving the seafront or they are not. And how do we use this technology? So we use it for short-term beach management as short-term beach management tools. So we started, my colleagues, they started measuring the pixels where we assume that people are on the beach. So it's not it's not sand, it's people in the beach. And for the last 2 summers, due to the COVID problem that we had, this technology has been really useful because we could measure using remote sensing with no one on the beach, measuring how many people they were entering to the beach. We could know how many people, the percentage of the dry beach that was covered by people. So the municipalities, they could decide when the limit of the percentage of the people in the beach to open or to close the beach. So this technology has been really useful for the beach occupation during the COVID pandemic. We can also use this in the short-term analysis for the beach safety. So we can give the information about the currents and the water movements, the eddies that we could have in front of the beach. So this is also really useful for the lifeguards in the beach. So they can be monitoring or they can be looking to specific points because they know that they are much more dangerous for the people, or they can assign some areas to surfers. But we can also use the technology, the same technology, but with different approach to analyze the long-term beach management tools. So as I said at the beginning, we can measure the coastline, we can detect the coastline, and if we can detect the coastline, we are capable to see the differences on the coastline, not only during different seasons, but also during different years. And we can also see the variability of the beach, of the supratidal, intertidal of the beach, and the distance of the water during the low tide or high tide, and during the different scenarios of the beach. And finally, we are also really concerned about the extreme events. I think that this is happening also in your coastal areas too. In the Spanish coast, we are having really difficulties to keep safe the coastal areas during the extreme events, and they are occurring more and more times during the last years. This is probably related, not probably, this is related to the climate change that it's happening, and we would like to at least to monitor and to give our knowledge to see if we can do something. So here you can see this is a time stack to check the overtopping. So this is the seafront that I showed you before. So you can see that the water is covering all the walking path for the pedestrians. And this is a similar approach, but in this case, instead of breakwater. So this is a harbor. This is the small points. These are the boats in the harbor. There is a videometry station in this area. So this is what they are looking. And in these images, you can see that we are observing we are applying or we are doing time stack images to these two lines, which are this one and this one. And you can see that just with the video cameras, we can observe how the front of the waves is approaching the breakwater. And in this case, we had an overtopping. So overtopping events over the breakwaters, we have to take them in account for the safety, not only to the people in the inner part of the breakwaters, but also for the safety and the maintenance of the coastal harbor structures and the breakwaters. This is the timeline. My colleagues, they started in 2007 using or installing the first videometry coastal station in the Basque Coast. And you can see that nowadays we have a lot of stations, coastal videometry stations. This is the Basque Coast. This is probably 120 kilometers in a line. And you can see that not only in beaches, but also in harbor areas. This one was the example of the previous one, the previous slide. We have cameras for different approaches. So not only for the monitoring of the morphology of the beach, which is really important for some beaches that are losing sand, but we also use it for the density monitoring, user density monitoring, safety of the harbors, overtopping. So you can see that in our coastal areas, we have plenty of those stations. And finally, as I told you at the beginning, I would like to show you these were examples of different remote sensing instruments and analysis that we do. But how do we implement all this information in a project, and for what? So P-Break is a predictive intelligence system to optimize breakwater maintenance. So this is a project funded by the Spanish Ministry and European Union. And we work several institutions on it. So AZTI, the Bilbao Port, University of Catalonia, and the Hydraulic Institute of Cantabria. We are, again, a multidisciplinary group. And the goal or the objectives of this project is to address the challenge of extending the lifespan of port infrastructure under a range of future climatic exploitation scenarios. As I told you a few minutes ago, we are really concerned about the extreme events that are increasing in our coast. We really need to monitor and try to extend the life of our structures. So what do we do in this project? So in this project, we first analyze the sea ocean state. So we needed to make an analysis of the waves and the currents in the study area. And we will apply novel sensors, all the remote sensing sensors that I have been presenting, to use this to extract the information, the real in situ or remote sensed but real information from the study area, to use it for the models that we will use to propagate the conditions from open waters to the breakwater to see what will happen, to anticipate and to propose maintenance, preventive maintenance to try to extend the lifespan of the structures, the infrastructures in the harbors. So this is a case in a specific harbor, but our goal with the project is not to focus on one single harbor, but use this information, what we obtain to any other harbor in the world. So what are we going to do? So this is the harbor. This is more than 2 kilometers. It's a big structure. We have installed few buoys. We have installed the coastal videometry and X-band radar at the beginning of the breakwater on the top. We have high frequency radar information from 5 kilometers to open waters. We will do topography campaigns using lasers to obtain the variability over the concrete blocks of the breakwater to see if there is any movement after the extreme events. And we will use all the information of the parameters obtained from in-situ buoys, high frequency radars, X-band radar, and coastal videometry to use as input for the models that will generate extreme scenarios, and we will see what happens. So we will try to analyze what are the worst scenarios for the breakwater. So this is just yesterday that they were installing the antenna, and this is how the coastal videometry antennas and the X-band radar antenna over the breakwater looks like since yesterday. So this is I think it's 12 meters, and there are another 10 meters to the ground. And this is what I wanted to show you, how we use remote sensing, not only to study for research, which is what I really like to do, to analyze the spatio-temporal variability at different scales in the surface waters of the ocean, in the coastal areas especially, but also to apply all the knowledge that we acquired with the remote sensing for civil, to help to the civil problems. And this is all what I wanted to show you. Thank you very much for your attention. And I don't know if you have any questions or.
Thank you for the presentation. It's actually a topic that we didn't have so far, so it's really interesting to hear all the techniques you are using. We already have 3 questions. So the first is which satellite data you use, and
so I will not tell you because I cannot remember them. I used them in 2010, and I cannot tell you.
Okay, and the Sentinel-3A, SAR mode, and JSON-3 have information about the waves and the wind. Do you use any of this data for your validation?
We used the Sentinel. I know that we used that one. It's not a specific validation because it's really difficult to validate, to quantitatively validate the information from the high frequency radars and the satellite due to the differences in the resolution. But we do qualitative comparisons, and we see that we are observing similar. I have a colleague, I didn't show his results, who is comparing the altimetry data from the satellite too, but I didn't show the results. But yes, we are using Sentinel data.
Okay, thank you. And do you use any data from tide gauges?
Yes, of course. We use that, and with the X-band radar, for example, in the port that I show you, we have thinking how the tide will affect to the X-band radar data, because we need to take in account the depth of the water, especially in the coastal areas. So we applied the tidal range that we measured in also in Biarritz in the last X-band radar deployment. And we are observing that using the information given by the tidal gauges is improving the processing.
And those equipment measures the sea surface height is the first question. I'm not sure about which equipment you mean, Marina. Maybe you can.
It's about the high frequency radar and the X-band radars. Those equipment measure the sea surface height.
No, they measure the sea surface velocities, the ocean surface velocities, and the waves.
Okay, you tell us before about the altimetry data, and one for your college's study about the Sentinel-3A. Did you publish any paper about this data and this study?
Yes, and I can try to find it. Yes, Ivan Manso Narvarte, he has several papers on that. So, I mean, if you want, I can send it later, or you can try to find his Ivan Manso Narvarte.
Maybe you can put the chat and Marina can copy it.
Okay, yes.
Yes. Thank you. And we also have a raised hand from Mr. Antoniadis. If you want to unmute your microphone, please feel free. Thank you.
All right, thank you very much. Can you hear me?
Yes, I can hear you.
Okay. Thank you very much for the presentation. It was very impressive. It's good to learn about new technologies, about monitoring the sea, and we are very interested in that. I have two questions. First question is that I know that your institute is very much involved in the Marine Strategy Framework Directive and the Water Framework Directive of the European Union. I have met Mr. Borja in many meetings. So I would like to ask you if you use this kind of data of all these technologies that you use for the monitoring of the European directives. This is the first question. I mean, if these the data that you obtain by these technologies are useful for the monitoring of European Union. And the second question is, because we are interested in the high frequency radar technologies, we had recently a presentation by the University of Hamburg about the VERA system. And people from there have made an estimation that Cyprus needs 4 systems of VERA to cover the whole exclusive economic zone of Cyprus. And we had made a cost estimation as well. So using this information, could you make an estimation about the CODAR system that you have discovered, and how many of these antennas could we need to use for our cost? Thank you.
Okay, so thank you for your questions, Konstantinos. So for the first question, yeah, so we are using the high frequency radar data, in fact, from AZTI, we are analyzing not only our high frequency radar data, but we are doing the reprocessed analysis of all the European high frequency radars. We are doing the quality control assessment to the data, and we are uploading the temporal aggregated files to the Copernicus web portal. So yes, I think the radar data that we are using, they are really European coastal monitoring. And for the second question, it's a really tricky question. Of course, we can sit later if you want. I mean, I think you can take my email. I would need much more information to know how many extensions you need. You will probably need the same amount of, if you don't change the frequency, you will need the same amount of stations using WERA or CODAR technology, because they both measure radial angle, radial footprints, and then they combine the data. The main difference is how they detect the angle. So you will need more coastline or most land area using WERA technology, because they install 16 radars in each station, and the CODARs, they install just one antenna, which is the emitter and the transmitter antenna. But if you want to monitor waves, you have more resolution with the WERA, because you have information in each pixel and not in all the circular area. The quality of the information is really similar. And I don't know, if you want, we can sit later. If you tell me the frequency that you plan to use and the area to monitor, we could have a meeting, a Teams meeting, and check if what they said it's logical or not. Or you can also contact CODAR, because I am really sure that they will be happy to give you an estimation of the cost and of how many antennas you need.
All right, thank you very much.
Are there any other questions? I will just wait.
Eleni, one question.
Yes.
Okay. First of all, congratulations for your excellent presentation, and thank you for the invited talk. One question about the beach occupation. Did you use any in-situ measurements to validate your results, or did you plan, or did you use, except from SAR technology, did you use also optical remote sensing? For example, did you apply any classification techniques, or did you use any artificial intelligence? Did you train any classification technique for the beach occupation? Because we are interested also for local use on the national level. There is a big request from national authorities, especially municipalities. We have some experience on this, but please elaborate more on which technique did you use, and if you use any in-situ techniques to validate your results on beach occupation.
Hi, thank you for your question, Diophantos. So this started around 2010, and my colleagues, I have not been involved in the beach occupation. It was a PhD thesis, few master thesis, and I know that they didn't use artificial intelligence techniques, but they used in situ data. They analyzed images one by one, and visually they also used classification techniques, and I know that they have papers. So again, I took your name, and if you are really interested, we can.
Yes, we are interested.
Okay, so I will send you the contact of the colleagues, so they can explain you deeper about them, and you can read the papers.
Okay,
I'm really sorry, I cannot say you more.
No problem at all. Thank you very
much. Because as I said at the beginning, it's not only my work. We are a lot of people in the team, so.
Okay, thank you very much. Thank you.
Okay. I don't see any other questions.
Hi from me as well. It's Kostas.
Okay.
I have one question.
Please.
First, thank you for the presentation. It was very interesting. My question is, it was a slide that for validation purposes, you compare your currents, your sea current velocities from the high frequency radar with observation you got from the buoys. It was a slide that you compare them at a single point.
Yes.
Would you able to give us how much error you have between the two methods? I guess you measure them in meters per second, the sea currents.
Yes. I am just trying to find the
slide.
Yeah.
And also, is it enough to compare your results with a single point? Did you compare the high frequency radar observations in a bigger area with the buoys?
Yeah. So thank you for the question. Thank you, because this was part of my PhD thesis, and it took really long time. So we compare not only with, this was just an example of the validation, you to see that this was a single point here. I showed you the Machichaco buoy. We did the same with the Donostia buoy. We measured not only on the surface, but also in deeper layers. We saw that during the stratification periods, we could see differences between the surface and the deeper layers, but there was, during the mixing periods, we could observe the intensification of the deeper currents also in the surface, and it was also shown in the radar. We also generated, we didn't deploy, but someone deployed drifters in the area. So we covered all the spatial study area with drifters, and we generated virtual trajectories. And after two days, we had few kilometers of errors, but the drifters, they were also moving a few kilometers. So the validation, the errors here, the differences between the buoy and the radar, they were around 10 centimeters per second.
Okay.
Yeah, and the measurements, they arrive, I mean, up to 80 centimeters per second in the study area, and the biggest error, they were that are up to 10 centimeters per second. So taking in account that what we are measuring with the buoy is a single point, what we are measuring with the radar, it's not a single point, it's an average of the radius and of the spectral data around 5 kilometers. And even the temporal resolution is not the same, because with the radar, we used few spectra before and few spectra after the time when we are analyzing the data, taking into account the differences of the data source. We were really happy with the results. And this is the results that other people are obtaining around the world. And for the spatial measurements, we did it with the drifters, and it worked. Not only with the real data, but also using forecast methods to forecast the data using the radar data.
Okay, thank you very much.
You're welcome.
We actually have another question. A lot of people are interested in this topic. Do you assimilate radar data to your circulation model?
No, we are still not doing that. It was planned, but it's really tricky, and we would like to go into that. I know that there has been a couple of trials. There are a couple of papers in the US coast where they did it, but we are not applying them in our model. But we would love to.
Thank you. I think that's all with the questions. So I guess we can finish for today. Thank you again, Dr. Solabarrieta, for today's talk, and thanks also to all the participants for joining us. We will be sharing the recorded video with you later on today or tomorrow, and we will be back with the next invited talk after the Easter break. So we are now taking some time off. Thanks again for joining us, and enjoy the rest of the day.
Thank you. Bye.
Bye.